Hey guys, welcome to Science on Air podcast, where we discuss some of the latest trends in science and technology. I'm your host, Ricardo Perez, and today we're going in depth into medicine, more specifically prosthetics and the materials used to make them. Our guests today are a group of researchers that specialize in such topics. I have here with me the lovely applicationist engineer Paulina Munoz,
Hi.
along with the experimental researcher James Wallace,
Hello.
and the mad scientist himself, Tristan Pepper.
Stay weird.
In today's world, we are faced with all kinds of different science and technology outlets of human advancements. Our topics today include biomaterials and applications. So, James, what are you working on today?
Chromium cobalt and how we can use it as a hip replacement.
Awesome. Sounds like an interesting idea or an interesting topic. So I did some research on the basics of biomaterials and the properties needed for it to be successful. I would like to share some of that information that I found for you guys at home. When talking about biomaterials, the most significant factor that separates it from any other material is the capacity to remain in contact with the tissue without harming it. For implants, this is no exception. It needs to possess important properties for long-term use in the body to avoid rejection. Mechanical and non-mechanical properties are essential for its design and selection of the material. Mechanical properties include hardness, tensile strength, modulus, elongation, strain, fracture resistance, and fatigue strength. Non-mechanical properties include high corrosion resistance, high wear and tear, and compatibility and osseointegration. So I would like to ask James, is this information that I give relevant? Because I mean, I'm no expert, but you guys are. Like,
It's definitely relevant. You basically hit on all the subjects that you would really want to look into when you're talking about, bio integration of any kind of material that you're going to put in someone's body. You want to know how everything's going to work, how it's going to function, what it's going to do. So yeah, I mean,
yeah. I don't want to give my audiences, false information either. So we prepared and conducted social media polls and questions about chromium cobalt that our audience would like to ask you guys. And our first question we have here is for Paulina. Paulina, what properties does the alloy possess that make it an ideal material for medical devices, and what advantages and disadvantages does it have?
Cobalt chromium exhibits some great properties that make it a practical material in the biomedical field. First of all, this alloy has excellent biocompatibility and increased tensile stress and high modulus of elasticity, which make it an optimal material. Cobalt chromium also exhibits a high resistance to corrosion because it forms a protective passive film on the surface, which is good, but it is still possible for it to experience corrosion. The two main ways corrosion can occur in this alloy is through crevice corrosion, which happens when there are cracks or gaps in the material, and Fredis corrosion, which occurs when the device undergoes micromotions, allowing small particles of metal to be released into the bloodstream, which causes health complications. Both of these ultimately lead to mechanical instability and failure. A big concern with metal implants are allergic reactions and metallosis, which is a type of metal poisoning that occurs when metal particles are released into the blood, which can trigger an immune response in the body. Another issue is that this alloy experiences low ductility, which is a concern since the material is commonly used in hip replacements and can fracture easily. Although there are some disadvantages that come with this alloy, its great strength and biocompatibility have made this an ideal material that is widely used in medical devices.
Thank you for your answer, Paulina. Next question will go for Tristan. If you had to pick two main mechanisms of failure for this alloy, what would they be?
Yeah, so when we're talking about the two main contributors to this mechanism, that's going to be for chromium cobalt implants. That's going to be inadequate corrosion resistance and a high elastic modulus, leading to load shielding, as it were. Basically, the first major mechanism of failure is attributed to the event of crevice corrosion occurring in small junctions between the parts of the implant. These micro-isolated crevices isolate body fluids, leading to a change in the chemistry environment around the implant junction. And this basically results in an electrochemical process that displaces the chromium ions from the implant surface via a cathode-anode reaction. And this electrochemical mechanism basically leads to not only the chromium ions being in the body in this chemical environment, but also further erosion corrosion. Yeah, I said that right. And then further degradation of the implant due to that. This depassivation process also causes a lot of other issues, a lot of other mechanisms of corrosion, such as cathodic corrosion, galvanic corrosion, etc. And so now we're talking about the second point of the failure. We're going to talk about chromium cobalt's high Young's modulus, kind of a pro and a con here. However, the Young's modulus is so high, in fact, that it overpowers the chromium cobalt's applications in native bone tissue, and it overpowers that native bone tissue's Young's modulus, basically taking off a lot of the loads and sheared forces that the bone usually takes on. This results in a decrease of the bone density, leading to the destruction and damage of integration tissues that are collagenous in nature, the regression of osteogenesis, the loosening of the implant, and increased friction, which leads to degradation of the implant.
Thank you, Tristan. I have a question for James. How do you expect to test for the rate of corrosion?
Well, essentially, we're going to employ a cyclic polarization method that will allow us to turn the test material into an anodic and cathodic portion of a battery. It'll allow us a chance to increase the rate of material degradation artificially, and allows us the chance to visualize graphically and utilize the phenomenons where materials tend to degrade or oxidize under specific anodic conditions. As for why we're going to do that, different parts of the human body will express varying degrees of microenvironmental conditions that an implant might undergo. Cyclic polarization allows us to adjust those conditions and produce sets of values that will better reflect conditions throughout the body. In this way, we can plan specific degradation events that may be beneficial in application. Some forms of beneficial degradation can allow for bonding surfaces to become apparent or more adherent and better utilized for the surrounding cells. So it also allows us to know that as well.
Okay, and how about what about the surface texturing? Does that benefit the product?
Well, surface texturing, what it does is it allows blastocells to adhere better to the surface, our osteoblasts to adhere better to the surface. It gives them a more surface area for which they can cling. Allows the implants to be more securely implanted over the course of the healing process.
Okay, and when we're talking about osteoblast integration, how would you plan to measure that?
Well, the integration of them is, since osteoblasts produce a cytoskeleton that is hard and rigid, the cells will be cultured on top of textured chromium cobalt surfaces. Then, after sufficient preparation and proliferation has been achieved, the cell will be lysed and cleaved from the bonded surfaces, which will allow us to sputter coat the cytoskeletons with a reflective metal and allow us to observe their structures in an electron microscope. We hope to see patterns representative of biometallic bonding observed in earlier works.
Oh, okay, and can you explain some of the specific mechanical characteristics that would be of concern if something such as a hip implant?
Considering the geometries of the hip joint, where an implant would need to be fixated, there are points of bending that need to be measured to ensure even strenuous activity would not cause adverse degradation of the material. Since this joint has a slight bend of approximately 120 degrees between the femoral head and the roughly center of the femur, that area represents continuous bending as weight is applied. So not only must the material be strong enough to support the human body itself, it must also be capable of supporting even more, all the while its crystalline structure must be retained in such a way as to not invite accelerated degradation. If you consider that while running for the force of impact can be many times the weight of the human body itself, from the conversion of G-forces to kinetic energy on the skeletal structure. This action causes continuous motion outward, and it causes continuous bending motion, like kind of outward, right? So it's important to know the elastic modulus of the material overall, but also know how the crystalline structures will deform. Understanding and knowing this information will help identify problem areas before they begin and allow us to plan accordingly.
Thank you, James, for your answers. And Tristan, I have one more question for you. Overall, how would you summarize the discussion we've had about chromium cobalt alloys?
You know, to echo Paulina and James, I would say that in sum, there are many pros and cons to using chromium cobalt alloys regarding hip, joint, and knee replacements. In terms of the merits of the alloy, I would say that the material properties exhibit a profound ability to integrate with native tissues, including bone, as seen in the process of osseointegration. The alloy is highly resistant to corrosion via passivation, which comes from the chromium. The material possesses a very high Young's modulus, which I kind of touched on earlier as far as mechanisms of failure go, kind of serves as a pro and a con. It has great toughness. The material surface characteristics in tandem with the combination of other metals that we can alloy in to the complex of chromium and cobalt provide a great biocompatibility. And so those are definitely some of the pros that I would consider when using this in the body. Now talking to the caveats, right, the negatives, I would say that there's two that come to mind. Firstly, the release of the toxic metal ions. This is common with most biomaterials, but in the case of chromium cobalt, it still does this. These ions in the body, which degrade out due to galvanic, fretting, and crevice corrosion, just multiple different forms that can cause this, cause severe allergic reactions, drastic immune response, and poisoning. Likewise, it's important to note that chromium cobalt's Young's modulus is very high and overpowers the native bone's own modulus. And in this case, a lot of times in the implant, this can cause a lack of bone density, as I mentioned, is one of the mechanisms of failure, leading to other issues down the line, implant loosening, etc. However, overall, considering our list of pros and cons, I would say that, and in considering the multiple tests that we run to verify these results, I would say that chromium cobalt alloys definitely provide a great biomaterial for the use of hip, knee, and joint implants in the body. And they are relatively superior to other materials out there and present opportunity for future use and improvement.
All right, and that was the last question we had. Thank you guys for taking time of your day to come into my podcast and answering these questions. I know they were kind of difficult, but it should have been piece of cake for you guys. This is all the time we have for today. Thank you for tuning in to Science on Air podcast. See you guys next time.